we are finishing all the light ray diagram of the lenses and mirror. We're finishing up to the eyes anatomy and thinking about what lenses we should choose for which type of the eye disorder. So if you haven't heard about hyperopia or myopia, we're going to cover it up too. So everything you're probably going to learn in school this week or the next week too, and possibly in your exams. Again, so we're going to practice these as we go. Okay. All right. Start revising with this, waves. Yeah, can you tell me what is what's waves?
It's something that transfers energy.
It transfers the energy, yeah, and it's not always acceleration, by the way. Well, it could be. Either be horizontally or vertically too. But there's one thing that you have to say, describe it correctly too. No. But what does it mean oscillations?
Sorry.
What does it mean oscillations? It's movement of going back and forth, or up and down. Do you remember like the slinky spring we tested too? What happens to the particles, net particles movement? When it goes up and down, the total displacement of the particle was 0. Same for the longitudinal waves, back and forth, the particle net displacement will be 0 too. So you need to say transfer of the energy without the net movement of the particle is what we defined the waves correctly last week. I'll go up to this point, okay? So you had a bit of like an examples too. We have discussed about the sound. I hope you did the question correctly last time, especially ear anatomy and everything too. You did good last time. You left in blank. I don't know why, what happened. Anyways, too. So we talked about sound is basically like a longitudinal wave. I showed the tuning fork. Hitting the tuning fork make a vibration. That vibration make the. It's all about particle like collision theory as well too. The particles, due to the vibration tuning fork, it will be vibrating or transferring the kinetic energy to the nearby particles too. Particles now be like rarefied or they're going to compressed, so that we are able to hear the sound. That vibration compression will be vibrating your eardrum, first of all. Eardrum is basically the thin membrane. So that's basically like a vibrating, the same frequency of the sound. That vibration will be like an amplify of the ossicles in the behind that too. When it goes into your cochlea, which is basically using the hair cells to transferring the kinetic energy into electrical energy. That electrical pulse goes onto your brain that we can recognize that there's a sound coming out to. Energy transfer without the net movement of the particles. Without. Sorry, my pen was running out. All good? So we have to discuss about some things too here. Now, the two ways we can categorize a wave as well too. One is called the mechanical, the wave. Another is called the EM or electromagnetic, the waves. Ryan, oh, where are you? Okay. Okay. Look, how do we differentiate mechanical waves to EM or the electromagnetic wave?
One needs a medium to hold.
Can you tell me what the meaning of the medium? This means the medium, requires the medium.
Like it needs particles.
Needs the particles to what? Transfer the energy from that. For example, we can think about sound. The water is a good example. Sound uses the air particles to transfer the energy. Water, tidal waves, using the water itself as a medium to transfer the energies to. Electromagnetic waves doesn't really not requiring any medium. It doesn't need any mediums to transfer the energies to. You may say like, oh, that's kind of odd. How do we get that to? But the way we can produce the electromagnetic wave, does anyone know how to produce the EM wave, by the way?
Like, isn't it made from the
Yeah.
like oscillation,
Oscillation of?
the electric and magnetic field, and they're perpendicular to each other?
Ooh, getting there. To produce, basically this is what we're using for all your antennas or your Wi-Fi system, radio stations too. We do the same thing as too. We're basically oscillating this electron or the charge of positive too. So electron will be moving up and down like this. Now, from the up and down, it has the wavelength, the frequency we generated too. Then this is called E field. That produces the sine wave going to this horizontally like this. As this is propagating to this direction B, this would have inducing some magnetic fields. You don't have to know anything about the induction yet too. That's the year 12 physics. This is why I don't really touch that too. But one thing that you have to understand, if the wave E, the E field goes up and down, like vertically, like this, now, it doesn't mean, one thing that you shouldn't forget is, it doesn't mean electrons going like this. It's not roller coastering. Electrons just over here, just oscillating in the same spot. They basically, this happens in your antennas of your Wi-Fi systems too. Or same for your mobile phones, receiving cells there. Electrons can be moving up and down using the AC. Then this will produce the magnetic field, which is perpendicular to this. And this goes like that. That's the magnetic field, we'll call the B field, the Gibbons too. What you'll be able to see here is that the E field generated from the oscillation of the electron, it doesn't really require any mediums too. Then, to increase the frequency, what we just do is we are increase the frequency of these oscillations too. And this is basically what we're using in radio stations. 101.3 gigahertz, 105.3. Those radio station numbers in the hertz is actually telling you about the frequency of those electrons oscillating inside that too. Receiver, we are setting up the receiver to be exact frequency of that 101.5. This is how you hear the very specific stations by matching up the numbers given to. Okay, so that's the things that doesn't really require the mediums. Means that it will be oscillating and produce the forms like that. Any questions about EM wave for now? B field is the symbol for the magnetic field itself. And inside of the EM waves, let's talk more about EM wave in here. We need to know about the property of the EM wave itself. One definite property you need to understand about EM wave is the speed of the EM wave is actually same as the speed of the light, but that is very specific in a vacuum or in a free space. Free space is the way we can describe in the vacuum space given to. So free as in like there's nothing. There's no particle, no obstacle given to. In this case, it's known as the 3.0 times 10 to the power 8 meter per second, also known as a C, the values. But one thing that you have to understand is it doesn't matter for any type of EM waves. For any EM wave, they were moving in the speed of light. Okay, the second thing is, if they're moving in the same speed, we all can have these some EM spectrums or EM wave, the spectrum of them too. The spectrum is not defined by the speed of the EM wave. It is defined by the frequency. And if you do remember the relation between F to the wavelengths, F equals to V over lambda, but in case of dealing with the EM wave, F will be same as a C over lambda like this. So both factors, it's either be like decided by both simultaneously decided by the wavelength and or the frequency given to. In general, we're saying lower the frequency, we're saying that lower the amount of energy they carry by them too. And this means what? The greater the longer the wavelength will be given to. So in the EM wave spectrums, you have ever seen somewhere that too, you may see like the frequencies getting increased and decreased that. The sections that we have are like in the middle, we have the visible, the light, with a very certain like frequency given to it. Now, visible light started from the really low frequency of the red, all the way to the violet and the blue. Before the red, we have a section called the infra. The red is a lower frequency, but longer wavelength. Infrared is the red. Infrared is before the red. UV, ultra, violet. There's the actual meaning behind the two. It's right next to the violet sections too. But what we determine that is, if basically they're moving the same speed. It's only difference of that the frequency of the given two. We can have the X-rays, gamma rays over here. We can have microwave, the radio wave, radio followed by radio, by the way, radio wave, followed by microwave there too. The reason why I said micro is that, yeah, microwave machines basically using the EM wave as well. They generate the EM wave itself. What do? Microwave is the EM wave. So how do we like heating up your foods using the micro machines? The microwave is basically carrying the energies from the heat, not the heat, the light. The light goes into the water vapors inside the foods too. They are vibrating. So that they're making the kinetic energy of those two. That's how to induce the heat. X-ray and gamma ray.
Is radio longer than microwave?
Is the radio longer?
Lower.
Lower, is it?
Frequency, yeah, and longer wave.
Do you have the? Do we?
I just saw while I was doing the homework.
I think I don't know. I might not be correct.
Pretty sure radio wave has lower frequency than microwave, but I don't know.
Because the sound
It
is,
has the lowest.
yeah, the sound,
Yeah,
the
you're
sound
right.
goes
Radio
radio
waves.
waves.
Microwaves, X-rays.
What?
I
Mhm.
forgot the middle part. I forgot the middle part though.
I just went from microwaves to X-rays.
And then, I don't know, visible light.
Ultraviolet,
Ultraviolet.
Such a ball.
What?
X-rays, gamma rays.
What are you on about?
Wait, there's a electromagnetic spectrum.
No, it's a micro and the radio. You're right. It was micro and the radio. Been a while. Okay, so that's the basically introduction of the EM wave. So what we are interested today, we're not going to deal with the gamma ray because I can't produce the. That basically means that radio is active one, and I don't have it. We do have some of the fire detectors, smoke detectors too. They do have the radioactive one. They have americium, which is the radioactive, the particles too. Don't worry, we're not going to deal with that. We're not going to deal with the X-ray because it's such a harmful one. UV light, as you know, is causing the skin cancer. I'm not going to bother to. So I will use visible light to talk about some EM wave properties too. Okay? No need to. So a few things you need to know about the EM wave properties as a given. You need to understand the properties of the light or the EM wave. In this case, we are using visible light today too. I'm going to use the light box that I should set up over here. This is chapter 5, by the way. Yeah. For the properties of the light, the two properties up to 3 you have to understand. One is called the reflection of the light. So let's talk about reflection first of all. Reflection, as you know, we can see like reflection that's going into on the mirrors too. So we're using a lot of times the application of the mirror today. So what is a reflection? When we have a really dense kind of like objects too, the light is not able to penetrate through inside. Instead, the energy of the light will be bounced back, goes like this. Now, one thing that you have to understand about reflection is called the law of the reflection. That angle made by the incident ray is always the same as the angle made by the reflected. So that's the incident, and that's reflected. But what angle we are taking is that we are taking angle from the normal, from the plane. So that's called the incident, that's called the reflected there too. Given that as I is same as the R all the times. So just like we bounce the ball to the water, depends on how angles that is going to bounce in the same angle it goes down to. That's the law known as the law of the reflection, that I is equals to R all the times given. And this is the key phenomenon to understand about the light and the reflections too. Showing you that, quick demonstrations. Ooh, kind of messy.
Is that all of our homework?
These?
This is the stuff we did at school.
Yeah.
Yeah, this is
So quickly show you over here. So boys, you can come inside, come over here to look at these.
Oh,
Sorry. So I have prepared a few set of the mirror. This is the mirror basically. You better come in and have a look. Okay. I showed a few things. Hmm?
Do you need to bring a pen?
No, just have a look. I showed quickly demonstrate like what I mean by those two. So having the light ray coming from the slit and just hitting the mirror here like this too. When this is hitting the right angle, it's kind of reflecting the same directions too. Now, tilting that, you'll be able to see the angle made from that incident is same as angle from the reflected all the times. And it's very basically, if I increase the angle, you will go like this all the way to here like that here. It's very simple law as you can understand. But what if we have a mirror look like this or that? Oh, we got to talk about focal point too. Even though we change the shape of the mirror, the rule about the law of reflection doesn't really get changed. What I mean is, if I place that over here, you still get reflected. Placed over here, you get reflected. You get placed over here, you get reflected as well too. So the way we can think about this kind of mirror, we have two types of mirrors you have to understand. This is called a concave mirror. The way you can understand concave mirror, or the curved mirror, is that instead of you thinking about this as the curved, think that as it's a multiple connection of the plane mirrors look like this. Then what happens is when the light is shown onto this point, it gets reflected back. Light shown onto this point, because of the angle of that, it will get reflected here like this. On here, get reflected, goes like that point. Go to even greater angle, goes then. Even that goes then too. Which is shown from that, as I'm moving these, you see that the point that is joined is always the same. I show the proof from placing this slit. Placing that to the plane mirrors, you would see that lights get reflected in the same angles all the time. But what about we place that as concave? You will see all the light will be joined in a one point over here. Can you see that? They all get reflected, pointing to one point. This is the point we named that as the focal point, sometimes known as focus. They're given to. Okay? Now what if we have this kind of mirror, convex? They look like this. It's easy. I flip that. This is a convex mirror. What you'll be able to see here is single slit. You'll be able to see the lights get reflected in the same manner of the law of the reflections too. Having the three, you may see light would get dispersed out, as like the lights get all reflected all other directions that it gives to. Can you see that point? What you need to learn is you need to know how those images will be displayed, and understanding that how those images will be formed, whether they be real or virtual or imaginary, inverted, upright. This is something we're going to discuss there as we go. Take a seat, please. It's chapter 5, by the way.
Why there no empty pages?
So a few terminology that you have to understand for today. Please write this one down. We have the symbols called the C. Okay. I just use this board over here. So started with whenever we're drawing the mirror, you have to be familiar with the mirror terminologies. So just write it down here too. Placing that in concave mirror, we have F, we have point called C like this. C, and we have point called O. Now, O is just simply means that this is called the optical, the center. Simply mean the center of the concave or convex mirrors that you have. F, as I said, is the focal point where all the lights get reflected and point and just join the one point. C is known as the center of the curvature. And this is basically, if you think about imaginary circles from here, this is center of the circle as well too. So we're taking that, the radius is r given from the kind of imaginary circle that we have. And the focal point, one rule you have to understand about that is the distance between from O to C, called the point is actually, and this is the focal point will be half of that all the times. So we have this F, which is known as focal length, is half of the from O to C, or half of the R, the radius given to. So that's the R, the radius of the whole curvature of circles given to. The focal point is therefore always decided by half in the midpoint between C and O. The distance between C and O is always the same. All good? Then how do we use that to draw the ray diagram for these? To understand the ray diagram, you have to understand the three rules. There are rays called ray 1, ray 2, and ray 3. Now, ray 1, you can understand it here. From the head of an object parallel to the axis towards the mirror, then reflected through the focal point focus. It's called the ray 1 given to. Sure, that what I mean by drawing the diagram look like this. Let's say we have convex concave mirror, placing that object in focal point F, and C is given here like this. Ray 1 is going like, starting from, I need to bring the ruler. It goes like this. From the head of your objects goes towards to the mirror, parallel to the axis, and get reflected and passing through the focal point that look like that. This is a ray 1. Good? Then ray 2 will be this. It's from the head of an object again. Okay. This time it is towards to the optical center. Then reflected with the same angle. Like this. From the head all the way to center of the optical center. Okay, goes like this. And then reflect with the same incident angles, which is going like that. That's ray 2. The last one, ray 3. This is one that still from the head of an object. Okay, passing through the F, the focus point, okay, then reflected by the mirror horizon, the parallel to the axis. Like this. From the head, it's now going passing that focal point in here, and then you'll be able to see that it's going straight or parallel to that. Now, after drawing the 1, 2, and 3 diagrams, you will see that all the reflected light will be pointed in at one point. This is where you get the image of your head, basically known as the reflected image, will be formed like this. And this is the objects that we have. Does it make sense to draw the ray 1, 2, and 3 of that too?
That's cool. If a teacher didn't tell us to do ray 2, then we don't need to do other things. 'Cause
Ray 2,
we only did 1 and
1 and 2, that's fine.
But for
Yeah.
the biconcave and the other one, she did the 3 rays.
1, 2, 3,
Yeah. But for the convex and concave, she did.
same thing. Yeah. Whether you get the 2 or 3, you get the same result as for 2. So the way we have to describe the image is that too. Now, what does it mean by reflected image? This is, if I see that, okay, have a think about it in here, guys, okay? If I place my eyes over here, I will see the reflection. Girls, this is something important. When you see the image placing in my eye here, because you see the 3 lights get reflected, ray 1, 2, 3, which means I'll be able to see those lights in different 3 positions like that. But when I'm looking those, I will see the image that look like this, 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 in 3 points of that too. Okay, so what we're going to see is the description of the image. Is something we do. You have to choose from the options there. Would this be real or the virtual or imaginary? Would this be upright or the inverted or upside down? Would this be diminished, magnified, or unchanged? So let's describe this image form the two. In this mirror, we have formed the reflected image in the same field of the objects. So we will describe that the image is real. Okay, as it formed the same views that given to, it will be the inverted, I should say. By the way, inverted. Okay, upside down, and size get diminished. It's the way we can describe the image form on that too. Does that make sense? Okay. Then can you draw 2-ray diagram for the concave mirror? One is a center focal point when we have objects in between C and F. Another is when we have the objects in CF inside the focal point like this. Could you actually attempt these 2 questions, please? Draw the ray diagram for when the ray and the object is in between C and F, when the object is inside of the F. So you may need to use a ruler and some pen or pencils. So that was what I showed you earlier. Over there too. When the object is placed out of the 2F, out of the center, so F is 2F. 2F is same as the C, basically.
Do you know how much sleep really well students get?
4 hours.
And it's not like they're getting that much more out of it.
4 to 5 hours. Yeah.
That's where
Is that like peak HSC time or just like
Oh no, they don't really do that much in during the HSC because we have like a lot of weeks, a lot of days of kind of spread apart. But during the trial period, which is kind of condensed the exam schedules to, I don't think they sleep at all. They do like a few hours, maybe like some nap, power nap.
we had a 1 minute pound.
Use the power nap. The 10 minutes or 15-minute power nap is really powerful. It's really useful.
Oh yeah, that's what my mom was telling me the other day. When
Yeah.
it gets closer to HSC, you need to start taking power naps.
Yeah, power nap 15 minutes is really good.
My brother takes a power nap, but when he when my mom wakes him up, he's too tired to wake up, so he just ends up sleeping in.
I know.
Isn't the second one not imaginary?
Oh,
Yeah,
would it be imaginary? Did you draw the diagram? Figure it out?
no, but Miss Cole said something about if it's
Yeah, that's something we're going to talk about too.
should I still draw the
Yeah. So start ray 1, 2, 3 again. Ray 1 from the head, parallel to the mirror, get reflected through the focal point. Ray 2 from the head goes all the way to the center of the curvature, get reflected same angles. Ray 3 goes passing the focal point and get the parallel to that. And, getting all that, you will get the points joined in one point over here. This is the reflected image. Okay, that's basically showing like what do we have in here. When we place that, something in the image out of that. Yeah. And you have to know why, in what instance we're using that property of the mirror. Okay, placing the object in between C and F, I can use that as a reference over here too. This is what's going to be happen. Did you draw something like that?
Wait, do we
Yep.
really need to draw the one going through the what?
The center here.
Yeah.
It depends, but in general, like just give me some syllabus point, we do run the 3 ray diagrams. What you only need to do, doesn't really matter. Okay, so ray 1, head parallel to the mirror, passing the focal point. Ray 2, stays in the middle point. Ray 3, focal point to that all the way to here. So let's describe this image. Look at what is the image? Would this be a real or virtual?
Real.
It's a real, in the real world over here. Good. Upright or inverted?
Inverted.
Inverted. Is that a diminished, magnified, no change?
Is it magnet?
It's a magnified. So which means if we place something in here, I'm going to bring the mirror later on too. From the concave mirror, if you're passing that center point, you will see your faces get enlarged, get expanded, but still upright, right? But interesting things, and this is where we're using a lot of concave mirror, is when you place the objects in between or inside of the focal point, like this. Now, ray diagram rule again. Ray 1, ray 1 goes from, ray 1 is from head to,
the parallel
to the mirror, and then,
to the focus.
but it seems like we have focus point too. So what we do here is you extend the line like this behind the mirror. Okay, ray 2, it is the one that goes in the center, and the gradient we're using that point like this. ray theory, Ryan? From the head too?
Oh, the focus point.
Yeah, but it's kind of weird, isn't it?
Use
So, yes.
dotted line.
So it will look like this. Connecting that to here, we can start from focus point and get reflected with the same axis that too goes here. It makes the image like this. So what is this image? Let's describe the image here. This is what we call the virtual. Okay, and this is the upright. Of course, this is the magnified. Now, do not get confused by the virtual and the real images too. Virtual simply means the image is kind of collected, all the reflecting point is collected in the behind the mirror. We are not able to see the collecting point. But this is something very important. Placing your eye over here, over here, over here, you're able to see the image of this arrow, big arrow, from the reflection of the given the object too. Where do you think we're using this kind of mirror then? Did you learn anything about this? Where do we use this concave mirror then? How do we use that? Where do we use that in real-day applications? No, not the microscope, that's the lenses.
Oh, you know the things in parking?
No, that's the other one too, which I'm going to talk about soon. Has anyone been to a dentist? Did you see like dentists like using the really the mirror look like this, with the long pole with the mirror? This is a concave mirror. What do? They place that near at your tooth. Wisdom tooth. Okay. So what? If placing really near at that, which is inside the focal point of that tooth, what you'll be able to see there is the image get magnified. And you can see from this view, as the image comes out, dentist out of the mouth, looking out of the mouth, will be able to see the magnified image of the tooth. So the teeth is something really small, but as they get magnified, they'll be able to see that which point they need to drill, they need to inject, they see like a point exactly to. That's only for the magnifications. But do not get confused about the virtual and the real images too. Virtual doesn't mean they're fake or something. It simply means the image will form behind the mirror. That's it. Okay? In this case of that, image is formed inside the mirror in the real world or the real field they're given to. But the important thing about reflection is if you place your eyes here, 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 you basically see that image formed behind the mirror that look like this the same times too.
Why did the rays like go to the end of like the axis and not just to the
Or where the axis here or that?
no, like the axis where the base of the mirror is. Like the vertical one.
Oh, here.
Yeah.
We're taking that as like a vertical axis of the mirror to like get the correct like a mirror diagrams too. So even though we have a concave mirror here like this too, we do use an axis to represent light get reflected from this point like that. Use the mirror here like this. There could be an error because you're not able to draw the exact curvature of the mirror itself. Because it's impossible to, unless you can calculate the values. Because curvature itself is kind of slightly different time to times, and focal length will vary by that.
If they give us the diagram.
Highly likely you get the easy questions then too. But in the practice one, we do like place, as I showed over here, highly likely a mirror would be more like kind of plateau, look like this. To avoid any things like any like a misconception, the misdrawing too. Are you all right? Wow, you're dying. Literally, you're dying. Okay. Any questions up to this point for the reflections too? Now, what about in convex then? Let's draw that. This is a convex mirror. They look like this, or I use a different axis that's given to. So this is a convex mirror here. Let's say we place the object somewhere here like this too. Now, convex mirror has curvature of the O is here, F is here, C is here. Okay, but the rule for the ray diagram applies exactly the same. So start with the ray 1. Ray 1 is from the head, goes straight parallel to that. Now, one thing you should understand it is it's a kind of diverse, it's diverging, so it will be reflected in this angle. But what you'll be able to see there is image behind the mirror is passing that the focal point. It look like this. This is ray 1 again. Ray 2, maybe in the center there too. So it will be passing that center of the curvature like this, going here. Again, the reflected, the same angle, the incident goes up, and we can connect this line to B. It goes backward. This is ray 2. Ray 3. From the head, it's through the focal point like this. So pointing that, it goes up and then get reflected parallel to the axis. That goes like this. Then you will see that in the behind the mirror, there's a point joining together too, which is forming the image of the head over here like that. Yeah. But one thing you have to understand is from the reflection of the light, if you're placing your eyes over here, you will be able to see that image, this image, at 3 different points at least. And this image is described as, this is the virtual, upright, and diminished image given to. So where do we use this kind of mirror? This convex mirror. Thinking back into the room that we're installing this kind of convex mirrors to, if we have someone standing over here, you'll be able to see that even if you're standing over here, there's a block, you're able to see the reflection of this person. When you're seeing the person on these civilians or the parking lots at the time to time, you see the cars coming from the corner because that's a dead spot. You can't actually see the cars coming. If there's a wall, there's a car parked in there too. But you can see the reflection that's coming to you as this kind of small image is given. This is how we use in the converging the lens is given, converging mirror is given. Again, concave, convex, converging, or concave. So kind of giving you like some ideas that it shows the image will be therefore forms like this, as I showed earlier, like this. Okay, and this is, if you think about it, it's a really powerful tools we can use because even though the object's really far away like this, because think about here, I'm moving this object away from the mirror. But the good thing is you can see that image still, but even though it gets really small too. So you can imagine about you looking there, the mirror installed in the car park, see someone's walking down in here, you see someone's coming in, you can notice that there's movements there. But you can't really recognize his face or her face because the image will be so small, the gibbons too. Because size would be about this much gibbons. Okay, that's the ray diagram rules for the mirror, both of the concave and convex. Any questions for this?
Wait, how come you did it like right on the mirror?
Around the mirror?
Like right on the mirror and not...
The lines of that too? Because my mirror here is quite plateau. I'm not really using the valve over here. If I need to use that, I know it's going to go up here. So in that case, I use the imaginary line of the gibbons too. Same of that. All good. This is how we use the mirror and the ray diagram. Then let's move it on to the next one then. Does anyone need a break? Bathroom, toilet? All right. The next point you have to understand. Huh? Do you need to go? You better go now. We have 1 hour to go then. Okay, the second property of the light you have to understand is the refraction. What is a refraction here? from what to what? Let's say we have water, okay, and this is basically air, the gibbons too. Has anyone had like seeing the fish underneath the water, in the water? That's a gibbons like this too. Yep, it's a fish. You can recognize the fish too. Now, sometimes if you're looking at the fish from here and try to catch that, you're always missing that because if you're pointing the fish the actual positions to, the fish is not really there. This thing's happening like the light coming from the fish goes in this direction here. You got to understand the point of the normal over here. That's called the incident. Okay, now one thing that you shouldn't get confused is the medium, the density is something that's very important to understand. What we know about N is the density, or sometimes known as the density, or sometimes known as the refractive index. That's gibbons too. What we can say is that N of the water is greater than N of the air. The water has a greater density of the particles than the air is subject to. Very simple. Then, one thing that you have to understand about refraction is this. Light travels slower in greater N. That light in the water travels slower than light in the air. It's very easy to imagine about lights get obstructed or get basically blocked by the medium, the particles there too. And here's what happened. This means if we have a light travel in the, you can rewrite it as light in greater, the bigger N makes the smaller the angle to the normal. What I mean by that is the fish coming from that, light coming from the fish from the water, it gets refracted in the air, goes like this. That's the R gibbons. But in our view, they're looking at the fish. It would be like this here. So placing your eye over here like this too. We try to see the fish goes into like that here. And then what do we have to see there is for the normal that's incident angle there too. The angle, the light is now getting more refracted towards the normals. So you will see the R's get over here like this. Even though the fish is over here, you will see the fish, we look like fish is over here. So in our view, we see the fish is here. Okay, or you may see the fish is over here like this. So you may understand, oh, we try to catch the fish, but fish is actually at the front, or like more forward than you thought the gibbons do. And this is proven by the law known as the Snell's law. So Snell's law. I was going to investigate this if you have the time, but it seems like we're running out of it. So N1 sine I equals to N2 sine R gibbons 2. That depends on the density of a gibbons. We have a given like depends on density of the N, the ratio. The I and R will be defined as 2. One thing that you have to understand is the greater the N, okay, smaller the angle. You don't need to worry about anything like formulas too. It's out of the syllabus for the year 9 for sure. I'm just teaching you year 11 one now. So don't worry about the mathematical terms. We just kind of understand the point too. Just try to understand greater density or greater refractive index, smaller the angle to the normal. All the times. Get more refracted. Okay? Then, I'm going to ask you to come over here to show the one thing. No, boys.
Say N1 sine I.
1 sine I, which is I is the incident angle, R is a refracted angle this time. Okay. Okay. Ryan and Luca, could you come and have a look at this one, please? So what I'm going to use here is that I'm using the perspex, which is kind of transparent like in the material or plastic itself there too. You see the light from the air goes into, and from here it get more refracted towards to the normal. Okay, but when it comes out from the normal to here, it get more refracted again too. So you see the light over here, here is a parallel. Light inside is get refracted. Is it okay? Okay. Same things happen if we use this kind of shape. You see the more refracted angles given here like that too. Now, one thing that you have to focus is this. Okay. Have a look. When I place that perspex and place in the angles, rotated angles, there is a moment that this angle of the refracted angle from, remember, from that light, the reason why we're using the round one is it doesn't really make a refraction inside of that too, because you're using the inside of this one. So you see no refraction happen. Placing that and rotating down, you will see the light in some sense will try to making into like this. All right here. Right over there. That's reflected in light. And now I have exact into almost like a 90 degrees. Could you see that? Angle made from the normal is never 90 degrees given to. Yep. Then exceeding that angle, you'll be able to see that light is not getting refracted. They are reflected internally. See that? There was a refraction reaching up to 90 by rotating this. And after exceeding that angle, you will see that light is no longer be refracted out. Instead, it gets reflected inside a given state. This is a phenomenon known as the total internal reflection. Have a seat, thank you. So let's have a think about it here. For this kind of conditions, you need to understand light must travel from the dense medium to the less dense, the medium. For example, light from the perspex or the water to the air. Like this. Had in perspex that givens the shape I showed, like what I showed earlier. This is the perspex that we have. Light goes into the round, doesn't get reflected or refracted like this too. So you see that this light in the perspex, this is called the perspex, and coming out from this to the air, you have seen that light to the less dense medium gets more refracted. So that's incident, that's a refracted too. Yep. Now, what you'll be able to see there is by rotating this perspex given, sometimes you'll be able to see like this. By doing so, the light gets exactly be refracted in 90 degrees like this. And to do so, I just use the same perspex, sorry. What I do, I increase the angle to more like this, and you get that. That's a 90, that's a refractive, and that's incident given as 2. In the case we get the refract when R is 90 degrees, this I is known as the critical angle, which is known as the IC. Time to time we were using that. Then exceeding this critical angle, here's what happened. Exceeding that, you'll be able to see the light inside going above the critical angle. So I is now greater than I critical angle here like this. You'll now be able to see that light is internally. The I is same as the R given to. The lights no longer be refracted coming out in perspex. They're more likely captured inside. This is called the total internal reflection that it be given to. Doesn't it make sense? Now, what if we have a series of this kind of perspex over here? So having this, having this, having this, and we'll be able to see like connecting this all look like this. Jenny, what do you expect if I have a series of this kind of perspex and then we can connect them like that? It's a bit of geometry, by the way. A little bit of that. What if we have instead of having one perspex of that too, what if I have series of this? Like this. I make the light get reflected, yeah? I place another one over here like this. And another one after. And what do we expect? The light inside? They're all internally reflected. Okay, so this is how we make the light, the fiber, which is basically using you for your Wi-Fi system. Okay, Wi-Fi audio network systems too. Okay, have you seen those like some Wi-Fi lines quite different to power lines of using the electricities too? They are basically reflecting or totally into reflecting the light inside the fibers given to and passing the data or the information through this wire. And we're using the total interreflection. Remember that to achieve that, I must be greater than IC to get the internal reflected inside of the this wire given to. All good? That's the you need to understand about Snell's law and the refraction that it's given to. All good? All right, then how do we use these lenses? I hope you can enjoy this, especially if you're interested about studying about medicines later on too. Lenses. There are two types of lenses you need to understand. One is the concave, the lens. Now concave time to time is known as the converging. Let me bring my notes again too. It's called a convex. Sorry, I should say convex lens is a better term. Convex lens. Or something known as the converging. The lens. Second type of lens you need to understand is concave. The lens, which is the diverging. The lens given to. And the shape of the convex and convex concave was converging diverging. They look like this. This is a converging lens. This is the shape of the concave lens or diverging lens given to. Then what do we need to know? You still need to know about the way of drawing the ray diagrams for the gibbons too. But where you can understand about concave lenses and convex lenses or convex and concave lenses, try to think that as this is two. We have two mirrors. So it looked like this kind of convex mirror added another mirrors too. So two convex mirror, the editor two, which means in this kind of the ray, we have two focus. One is coming from here, and it's from the here like this. And basically, what happens to the light is for the converging, when the light goes in, and we use the imaginary axis in the middle here like this too. When light goes in, they get converging into the point, to the focal point and the next adjacent point too. Vice versa, if we shoot the light from some of the point, from here, it will converge through the focus at the other side of that image. Okay, so what do we able to see using, what do we get from the convex lenses or converging lenses is the image from here getting shrink down. Diverging is kind of opposite to it. Still, we have two axes. We may think about this as a two concave mirror. that will have the focus point over here, F and F. So here's what happened. Shedding the light to this focal point of the to this kind of mirror. What do? They get diverged out. They get diverged out, and the angle is basically depends on the focal point here, like this. This one too, the light goes, and from the focal point it goes outwards. Could you see the purpose of focal point too? Same for the light that approaching to here, it goes to that and get diverged through this angle. Same in this, get diverged from the focal point like this. All good? So let's draw the ray diagram for this lenses then given to. Start with the ray diagram rules then. Ryan, what's a ray 1?
Do the focus and then reflected parallel to the axis. Also, do
Yep.
parallel to the axis and then do the focus.
Yep, so let's do the same, use the same rules for this too. I have the convex lens here. Focal point F and F. That's given here like this. And we have an imaginary point. We use the midpoint to show like a reflection of that too. Ray 1, let's say we have an object located over here. Same the objects. From the head of the objects, it goes towards to the mirror parallel. Yep, and then what happened? As it's a converging lens, it will passing through the focal point in the behind of the lens like this. Ray 1, same rules applied in the parallel, and they go through the focal point. Ray 2, or may have been ray 2 too. It's from the head, it's going into the center. Now, unlike the mirror, if it hit the center of the lens like this, it just goes straight without any refractions. So it will be shown as this. This goes up like this. Ray 3, or sometimes ray 2, from the head to ray 3 or ray 2 in school, from head to focus. Which one? We're using the first one here. It goes like that. It goes up like this. Okay, and then parallel. That's a ray 3. Then you will see an image with a formed look like this. This is refracted image. So what do we have to see the refracted image here is they are inverted, but would you consider that, Jenny, would you consider this refracted image be real or virtual? Oh, it's a real. Okay, now for the lenses, image must be formed behind the lens because that's the purpose of the lenses too. They need to transparent or they can passing the light through. So image formed behind the lens, image is formed behind the lens. It's a real image that too. Still be like upright, inverted. And we have that, I think it's about the same length given to, there's no change in length. And basically, guys, this is the lens that you have in your eyes, in your eye lenses too. Not my specs, inside of your eyes, in the cornea, inside the cornea. Okay, are we good up to this point? What about the diverging, which is a concave lenses they're given to? Do the same thing again. Diverging lens, they look like this and have a focal point in the middle here. So we have a focal point and focal point over here like this. Let's say we have an object that looks like this too. Look, ray 1 from what to what?
From parallel to the focus.
Yep. So it goes we gotta take an imaginary, like a midline over here. So I use the ruler to take the midpoint. From head, parallel to the lens. Now, as this is a diverging lens, it will be diverged from the focus, look like this. Goes above. Okay, still passing that or using the focal point. All good. Ray 2, in the middle, it goes in through the center. It will actually pass through the center here like this too. But what we're seeing that is the some light get refracted through the point like this. Okay, I should extend that ray 1 again too. So ray 1 get extended. Seeing that lights get ray 2. Goes at the point. Ray 3. From the head through the focal point, so it will be like this. We use the second focal point, so light goes all the way to here, and then gets refracted parallel to this line. Okay, and you see some, it's actually like an odd too, so going into that. It's my diagram too. You will see the point of joining here like this. Let's actually use that. Here we go. Inside of the heel like this. So ray 1 again from the head, go to the parallel to the this axis 2, passing the focal point. Ray 2 straight down. It's actually going down here like forms 2. Ray 3, which is this. It's using the second focal point behind the 2 and the good parallels. Connecting all of that. Sorry, my diagram is kind of off, but it should look like this. We're saying that all the refracted light and some light get connected to. Now, describing the image here. This is not a real image, even though we have image form inside the same axis that too, because the lens must have the image form behind the lenses too. This is a virtual, but upright, and giving them to be what? To be diminished. Will be given. All good? So that's the purpose of using diverging lenses. Means that if you're looking somewhere in here, you will see like a lens image will look like this, refracted. Then how do we use these lenses for the specs? Does anyone know the difference between hyperopia and myopia? Okay, kinda, never. Okay, we're gonna learn today then too. I just started from this anatomy of the eye. I will give a really simple one. Eye look like this with a bit of like cornea sections too, eyeballs, and we have the optic nerves at the back. It has the section called this region called the retina. Okay, this is known as cornea. Okay, and inside of that we have a lens. Yes, Ryan, can I help you? Okay, this is the simple anatomy of the eye. Of course, there's some capillary muscles, iris, or some other things too, but you only need to know these for now too.
What is that thing on the right side?
Retina. So you might have heard about retina display, look like a human eyes, because you're using nerve receptor too.
Max say that.
Yeah, Max say that. Okay, now how do we see something then? There's something you have to understand. When we place something over here, look like this, the light coming from the, this arrows goes to all the way to the cornea, the top and bottoms. First things, this lens over here from the cornea is a lens. It's kind of too bulky. The lens look like this. Okay, yeah. Would you consider that lens of the cornea be concave or convex? Or like a diverging or converging? The shape of this, would this be a concave or the convex? Concave? The shape of that
Oh my god. Convex.
is a convex. So is that the converging or diverging? Boys, convex, diverging or converging? Converging. Diverging always diverge that light. So the light goes from the cornea, get converged first of all, goes the hitting up this point. Okay? It first get refracted. Then we have another lens, which is the type of the convex lens given to. What do? They will get convex too, so it goes all the way to here like this. As it's passing the focal point behind the lens, we have seen the image is therefore behind the left retina, this section over here, to be formed like this. And when this image hits right spot retina, you're able to see that image clearly. Same size of the hands. All good up to this point? Bit of biology sessions you need to understand. Well, everything's related. I can bring it up chemistry here if you'd like to.
Wait, how?
The hormones.
Isn't that technically? Oh wait.
Technically, hormones are chemistry. It's all combined, basically. All good. So you're able to visually see something when we're seeing that the image is formed behind the retina here like this. I'll show you two symptoms then. Okay, who's wearing glasses? Anyone else? Glasses or the contact lenses? Contact lenses too. Now, are you like, let's ask you here. Look, are you like long sightedness or the short sightedness?
I'm really short.
Short sighted. So what do you mean by the long short sightedness? Can you see something far without the glasses or the near?
Sorry?
Can you something like, if you see like take off your contact lenses, would you be able to see something really far or the short? So the common mesh disorder is here. We understand myopia. Its common name is the kind of terms we use in the medical terms too, but in short terms, it's just like in real day term, we're using as short sightedness. It's called a myopia. We have the hyperopia, known as the long sightedness. Charlie Brown. What's Charlie Brown?
Oh, like the character of Snoopy.
Now, what causes the myopia? So you may see like something like disorders too. This myopia will be formed, the lens or the cornea is too elongated. It's basically known as the too elongated. In other words, shorten the lens that we get. See what happens if you shorten lens too? Guys, this is what happens if you're watching too much YouTube in the dark night too, before you go to sleep, basically. I'm talking by myself, okay? That's what happened. Seeing the eyeball with the cornea, eye structures given to, we have a lens. Now, if you're watching too much YouTube in the late night, your eyes, as you see something really close, you're using, think about here. If you want to see something really close to, you are basically shrinking your eyes. You don't really open your eyes wide to see something really close. If you want to see something in your fingertips, you have to shrink your eyes. Now, shrinking, making that lens be contracted. So if you had persisted doing that in the late night, what happened is lens inside will be really shortened like this. Elongated like a...
Wait, so is it
elongated means like, it's eye shape is too much elongated. Don't worry about it here. Eye shape is elongated, that gibbons too. Don't worry about it here. So you may just understand, let's select that, it's better to say here. The lens get shortened or the contracted. See what happens then? As lenses get shortened too, see this is what happens. If you have an image that forms here, it goes to the cornea, okay? And then once it gets hitting that too, it's passing that, or maybe passing that too. So here's what happened. The image will be formed over here. Even before it hits the retina, due to the shortened lens, the image will form behind that or in front. So image will be formed. We describe that image is formed in front of the retina. What about hyperopia? Okay, do you know who's experienced the hyperopia, the long-sightedness a lot? There's someone like who can see like something really close a lot.
Doesn't Veda have?
It generally happens to the when you get old. The elderly cannot see like really old is like going to like the 90s and the hundreds too. What happened that is as their eye muscles get weakened, they can't really contract the lens properly too because the muscles get weakened. So the lens almost like be like stretched a lot of times to give it here. So this is lens. Lenses get the stretched.
Then if my lens is too short right now,
Yep.
then as I get older, and then they become, will it like no, will it make itself normal?
Not really.
Oh.
Because what actually happens, you get adapted throughout the years, your cornea get reshaped. Have you seen, look at, for example, my eyes, I've been wearing the glasses for like more than 30 years though too. It's basically like my eyes started, eyeballs started getting popped out.
Oh.
Yeah, it actually happens too. I don't want to show you, but you can imagine that too. Because it's getting adapted to the, giving that to be, to capture the light. My eyes try to get forward to get the light more efficiently.
What if I just widen my eyes every day for like a year?
What can you? Isn't that better to get a cosmetic surgery, cosmetic surgery earlier too? But there is some of the LASIK surgery basically on using that, or the contact lenses as well too.
What's this LASIK do? Does it stretch it?
Well, it doesn't really mean like you can see the vision properly too, because you're not really affecting your cornea. Instead, you're just changing the shape of your eyes. That's all you do.
How do the contact lenses that work at night work, like the ones that push you?
Oh,
They reshape
you wait. I'm getting there. Okay. Over here, we have a cornea. They look like this here too. Now, if the lens is too elongated like this, or like stretched, there's a shape of the lens. Guys, have a look. The light coming from the objects hitting that goes into here like this, and then what happens is they goes behind that. The image is now be formed behind the retina. As the longer stretched lens means that the focal point of the lens getting more stretched, going behind that. This is the focal point. So we see the image will form behind the retina. Yeah, that's what image is formed behind the retina. So let's discuss about one thing here. In a group, if you have a patient who's having this kind of symptoms, myself by the way too, what type of lens would you suggest? Would you give him concave or convex? Start with the myopia. No, only one. I don't want to wear two. Give me one. No. If you get convex or concave, think about it. What if we get concave? What if we get convex too?
Wait, aren't lenses just like one way?
Wait, do you have lenses as well?
Do you have lenses?
Convex. You have, right?
Yeah, okay.
Do you?
Yeah, we're gonna talk about dream. Is that dream lenses you're talking
Yeah,
about?
yeah.
Yeah, we'll talk about it as well too.
What?
Wait,
Why
are
do you
lenses
all
just
have
meant to be
lenses?
concave?
Concave. Wait, what?
Like-
I swear I've never
Like the
seen
part,
you with glasses.
like isn't it meant to match the shape of your eye? So like the part that's curved is like on your eye. And yeah, so how can lenses
Bro, I
be
don't know
convex?
this. I don't even know what degree I
Wait,
am.
that's kind of
Yeah.
wait, that's kind of true.
Like if
I
it's
don't even know what
convex,
degree I am.
Put it in your eye and then it's gonna be bulging out of your eyelids when you close your eyes.
Wait, that's kind of true. Guys, what's the
So you made a decision, guys. I need a prescription. Tell me what should I wear?
Just wear glasses.
Just wear glasses, like the blank glasses, which it doesn't have any refractive power. Really? You're a terrible doctor. Okay. Come on, Jenny.
What? I'm like the one person here who doesn't have lenses. Why are you asking me? Wait, but aren't all lenses shaped the
Well, you're not gonna complain like I'm not wearing lenses, so I can't give you any suggestion for like what lenses you have to wear.
Lenses shaped the
Yeah,
same.
but aren't all lenses shaped like this though?
No, they're quite different too. Like I know they're shaped like this.
Put it on every the other way.
You haven't seen the granny's like lenses ever, have you? Have you seen the granny's lenses? If you have a chance to later to have a look at the lenses,
Can you show us?
you can go to pharmacy and actually seeing that too.
How do you put on convex lenses if they stick out of your eyelids when you close them?
I'm talking about specs, like your glasses, or like
It's like contacts. Like
contact lens, the same things as well too.
what the?
But contact lenses basically. Why is it contact lenses? Because you can stick onto that too.
Your eye is shaped like this. How do you do it if it's like?
Don't ask me. I'm not an engineer. I'm building that too. I'm a science teacher. I'm a science teacher, not an engineer. I don't care how they do it. It's not important.
Wait, so convex, right? You can have convex. We just agree on convex.
Convex contacts.
Which one? For the myopia, convex or concave? Justify it. By the way, justify it.
Both of them are convex,
Both of them.
otherwise you can't wear it.
But wait, but aren't they technically both concave and convex at the same time? Because if you flip it, it's like concave, and if you flip it back, it's convex.
Oh
No.
my God.
But
It's
how
not
do you,
how the
if
light
your
hits
eye
it.
is shaped that way, how do you?
Yeah.
Guys, what is the issue with the having the myopia? The lenses get shortened or contracted. Okay, sometimes we have a surgery of the replace the lens itself.
How do you do that?
You just cut your eyes and then you take the lens out too and replace with the artificial lens.
Ew, sorry.
Wait, is the lens?
That's actually legit like some person
That one
procedure.
friend
What is the
posted-
lens made out of?
Lens is made of the That's a good question. I'm not too sure about what it's made of too. But what we're putting in there is made with some silicons and the plastics too.
What is it? What is the original lens made of?
It's a fibers, collagens. So we basically replace that with artificial lens, but that's not the case I'm talking about here. We can't fix the lens. I mean, like you can replace that. It's kind of dangerous as well too. You can imagine like cutting your eyes and putting the lenses back into. We do that if we needed to, but and especially with the cataract in the patients too, who goes the lenses get blurry, they can replace the lens itself. What if we're here? The issue is this concept is the lens of the cornea is get damaged too. It's hitting that in the middle of that too. What if we can stretch that? So, recommended lens for the myopia is diverging. Now, how do we do it? Placing the object over here, here's what happens. As the light hits the lens first, it gets diverged. So it will be hitting the edge of the cornea, not in the middle. Then it will get contracted and edge of the lens. And then they will be able to hitting the retina over here like this. Kind of extending the light using diverging lenses. And that's what I'm wearing. That's what you're wearing. Then how do we do the dream lenses now? Good questions though. you don't do the lenses. Over the night, when you're wearing lenses, you're making the reshape your cornea. But do you think your cornea needs to be reshaped as in like stretched or contracted? If you're myopia, short-sightedness, you can't see something there far. Do you think you need to stretch your cornea or contract the cornea? Stretch the cornea too. This is what happened during the night. Okay? Yeah, that's basically what the dream lenses do. They are given the pressure to reshaping the cornea structure of that too.
So is the cornea the whole black part?
No, it's not basically like the cover part, the surface of the eyes too. Shouldn't touch it. Anyways, that's a kind of lens kind of shape.
It doesn't have it.
Does it make sense to all two? Okay. What about in hyperopia? What's the issue with the hyperopia? It's too stretched. So what do we have to do is, we can't fix the lens, can we? So we're placing that into this kind of lens. See what happened? Placing that concave, the lights hit over here, get refracted, get refracted, and then we can shorten. So, question. This is one of the reasons why we don't have many of those contact lenses with the convex lens too. As I said, this is mainly experienced by a lot of time in the elderly people as their muscles get weakened inside of the eyes too. They can't really shrink the eyes properly. So they're wearing, this is why they can see something really in the short sight. They can't really see something really close. So they're wearing really thick glasses which have this kind of the converging lenses.
Wait, does it mean if you have already bad eyesight by the time you get old, you have to wear glasses like this thick?
Well, yeah, highly likely to. Now, answering back to your questions here, you already have myopia. Now, as you're getting old, you get the hyperopia. Too bad, I'm sorry, we can't fix both. So what actually happened is, have you ever seen like the glasses with another glasses over here? There's a kind of glasses known as a multi-focus glasses there. This is the convex. This is concave. Ask your dad. I think they should be the expert by now this time too. I might get this one when I get old. Okay. Let's talk about one surgery too. Has anyone heard about LASIK surgery? Yeah, what's a LASIK surgery? To make you see like something better, okay? Without you making up to wearing the glasses anymore too. But what is a LASIK? Has anyone, okay, you're not done the LASIK. Probably do after you finish the HS, I guess. LASIK. Plan to do any LASIK surgery?
What's a LASIK surgery?
You don't know LASIK surgery, okay. Do you know what the LASIK surgery is?
Yeah, but I don't need it.
I know you don't need it, but I'm just asking, do you know that?
One of my dad's friends got it.
Yeah.
How is it one person who doesn't need it know what it is? But
Okay, LASIK surgery is a type of surgery that we are reshaping the cornea by cutting that using a laser. Yeah, the reshaping the cornea, not the lens, cornea. You're not touching the lens because of different surgeries that given to. So by reshaping that, have a think about it here. In the problem with the myopia, we have to see something that really close to in front of the retina. How do they need to reshape the cornea then? How should they cut the cornea, the reshaping the cornea? Like an architect, you can think about it too. It's a bit of sculptures, they have to do it.
Are they gonna like flatten it?
Flatten it, why?
Because if you flatten it, the focal point.
As your flatten it means focal point will get closer or further.
Closer.
Oh?
Oh, sorry.
More flat lens means more further apart too. Having that issue with this, as the lights get more further apart, it will hit the edge of the lens. Therefore, you can fix the vision problem there too. The issue with the LASIK surgery is because you're touching the cornea too, there will be some side effects, dry eyes, basically, they came to and once you've done it, there's no go back. You're gonna leave there forever, basically too. Same for the LASIK surgery, hyperopia, time to times too. Okay, this is the reason why I'm interested in eyes and with the lenses. This is a perfect example of the understanding converging and diverging lenses. And some of these is a part of your outline, by the way. The eye structures and the eye of those two, specs and the lenses. So you're three wearing the contact lenses. Highly likely you're wearing this concave. Okay, any questions about these?
Does that hurt when you sleep?
No,
Do you
it's
ever
like-
wake
like-
up and be like, oh, my eyes hurt?
No,
It
my
hurts
eyes
so
are
much
just
on the
always
first
dry.
week. On the first week, I was literally crying.
On the first week, it hurt really, really much, but you get
Do
used
you
to it.
order dream lenses?
Really? That hurts?
On the first week,
Does
not
it?
anymore.
Oh yeah, because now you know why it was so painful.
It's reshaped.
My one is only because my eyes became really dry.
Yeah, why? Now you know why.
Please, eyesight don't go away.
My brother would punch my eye when I was wearing it.
Punch your eye? What?
Oh
was
wait,
wearing
I
lenses when I
forgot I
was
have to wear brace elastics. I like haven't worn them in like 2 weeks.
Why'd you have your dream lens if you weren't going to sleep?
No, when I woke up, he just punched me.
What the?
You punched me?
My brother.
He just went to your room.
In my on the eye, where I was wearing my lens.
Oh.
Wait, one time I like smacked you on accident with the eye.
Guys,
Okay.
does that hurt when you put it in? Like,
It's really uncomfortable.
when you like,
It's, when you put it in, it's like slightly
Well,
uncomfortable.
for me, it's actually.
When you
I
take
have
it
to-
out, it
I have to-
feels really good.
Okay, let's do some practice questions then. I will talk about the so human basically like all those dispersion and star colors too. Luca and Nia, have a look at your page workbook from the chapter 5, page 20 and 21. Last page, yeah, 20.
I think Ginny needs to sleep.
Yeah, it's going really bad
Yo,
now.
You slept like the second earliest. She was one. two.
5.14, the question. Did you find page 20?
What type of mirror creates a light?
Did you find page
What
20?
time do you sleep?
5 questions.
I forgot. I slept like 15 minutes.
Wait, where is it?
And probably woke up.
Page
at
20.
Is this
Chapter 5?
Yeah.
Are you sure it's chapter 5?
Yeah.
Behind.
Oh,
Oh, behind that exam practice, we have some questions. You can find it behind. Keep moving. No, it is chapter 4.
What? It says part 5.
Yeah, but could be wrong. No, it's part means up out of the chapter 5 of part. So you've been using the wrong.
when she, yeah.
You don't have any side effects.
5.14. Jenny, you're not the only one wearing the context too. Don't even think about wearing context. It's really uncomfortable, by the way. So keep your eyes healthy.
How are your eyes so good?
How are our eyes?
It's genetic.
My,
Oh, yeah.
my eyes used to be good before I started.
you know, my parents' biggest threat to me when I was younger, because I kept reading in the code and stuff. They're like,
You're gonna have to get contact lenses when you do if you do that.
Well, isn't that a thing?
That's
when
what my
you,
mom
like,
said. I kind of regret it.
My eyes used to be good before selecting. I wonder what happened.
5 questions. Let's do it.
a blue star is.
It's a blue star. 5.14.
Why is there a blue
Isn't
star?
it?
It's a blue star.
Oh yeah, we can talk about that too.
What's redshift?
Oh wait, no.
Oh, it's
The
the
other
other
one.
thing is a divergence, right?
Wait, what? Wait, oh, we're still doing waves. Wait, isn't this waves? No way.
This is a wave.
Which type of mirror creates a wide field of view?
The blue star is.
Okay, when did we learn?
What the?
Well, it's hotter than.
Well, a blue flame is hotter than a red.
We
orange.
kind of did in EMA spectrums too. Even though we haven't, it's not specifically about the stars.
Wait, that,
What's an inverted mirror?
that's concave.
What? Oh yeah. Wait, say mouse.
Yeah.
Which one's convex?
One that's.
Oh yeah. I keep. What is redshift?
You.
We have to do Doppler. I will do the Doppler next week.
A short-sightedness is correctly. Are you short-sighted?
Are you short-sightedness?
I think all of us are short-sighted.
Yeah.
Yeah.
About like 90% of the people are short-sightedness for the young
Maybe
peoples.
It's like, an exception. Wait, really? Wait, I
Oh,
thought
long-sightedness was more common.
No.
What?
Short-sightedness. But you know how people say it's blurry, like the board is blurry.
Yeah.
When you're sitting at the back, that's short-sightedness.
Yeah, it is. Not bad. Not bad.
What is red shit?
And let's take an educated guess.
Yeah,
It's probably
red
not
is
this.
like on where the wavelength is longer and frequency is shorter. Right?
It's probably the universe.
But I don't know.
Red,
shorter.
red has
Frequency
the
is,
longest wavelength of
yeah,
the
red
visible
has
light.
the longest wavelength.
Yeah.
It's
Why do
probably-
your eyes turn like red if you don't sleep?
Well, the universe.
During sleep,
If you
Well,
don't
logically, the universe.
you don't
is
sleep.
expanding,
Why
so
eyes
it's
goes?
just gonna be-
sleep.
Your
You know how it's like red?
your eyes go red.
Yeah.
If you don't go to sleep, are you enough moisturizing your eyes enough? As you open your eyes more in more greater period of time, your eyes can easily get dried.
Light bends to-
And also, it's also affected by like
Isn't
the
it
blood
into a
pressure.
less dense medium?
Mhm.
Blood pressure is affected by
Oh, we're
sleep.
done.
Of course. It's like here.
What's the normal here?
If you don't sleep, can you run 100 meters really quick?
No,
No. Why?
because you just can't. Because you're tired.
What, you gotta think of like, some medically behind it too, scientifically.
Where's the normal-
It's all related to like a pharmacology later on too.
Like,
What
where-
medication you have to prescribe and that what reasons too.
Then it's just
When you're
control.
tired, your heart rate is not normal. Your heart pumping kind of slow. Because you gotta understand, like your brain's kind of consider that as
No, when it said light
that,
must
oh, we
travel
have to go
from
to
less
sleep. So
than
they
two
try to
to
shut that down.
So it can't travel from a less than to.
But what happened is you're consciously then try to wake you up. So you're making the drinking a lot of coffees, the caffeine that kicking into. Your brains are like forcefully awakened. Then,
What the?
as you have missing the time of the resetting your blood pressure and the heart readings too, they are pumping really weak, making the blood pressure rate dropped.
Your vapor is more dense than
And in that sense, when you're running while your blood pressure dropped,
more dense than
you get fainted
water, liquid water.
because you don't get enough blood to your brain. There's no pump, there's no pressure. So don't run when you're not sleeping.
I can use that as an excuse in PE.
No,
If I run my blood
would they
pressure
listen?
too low,
Okay.
I'm gonna die. I only slept like 15 minutes earlier. What are you
You said 2:45. You said it's at 2.
2:45
No, I would
is
have finished
too-
at 3, but the Dream Manhunt came out.
Bro. Couldn't you have watched it like
Question
later?
1. Which type of mirror creates the wide field of view ear? Question 1.
B.
Concave mirror?
Oh, mirror.
It's a mirror, not a
Oh.
lens.
Wait.
Convex. Wait.
Oh wait, we had the right one. We just put the wrong answer.
Wide field, which is convex. Where do we use the convex lens, the mirror? The parking lot, the civilians, all the purposes too.
What do we think?
It's not lens, it's a mirror, guys. Okay. 2. Blue star is okay. Shh. Blue. Compared to red, would you consider blue to be a higher frequency?
Yeah.
Yeah. So higher frequency means more energy. More energy means greater heat. Simple. So that it'll be hotter. It's actually hotter than the sun. So the C is the right answer. Sun, by the way, is a yellow star. It's only in between red and blue. It's in between in the yellow, which is like moderately, still extremely hot. You know, if you get some baked, you probably know what I'm talking about too. But relatively not. Okay. 3. Short-sightedness is corrected using. So we all short-sightedness. What lens would you just prescribe to me? Concave, diverging, which is concave lenses. Okay, guys, it's very confusing. Concave, convex, diverging, or the converging too. So try to get it right too. Diverging is basically concave lenses. Converging would be basically convex lenses given.
It's a concave mirror, a converging mirror.
No, there's no
But
concave mirror is kind of converging, like getting the light in the focus to, and this would be basically diverging to. Kind of confusing, I know. So it's better to like memorize the shape of the mirror and the lenses to try to memorize those like kind of properties it given to. Redshift, don't worry about it, but I can give you the answer. This means that the universe is expanding. Answer is B. Redshift is, by the way, is the evidence of the Big Bang Theory. The redshift of the galaxy is the evidence of the Big Bang Theory.
Big Bang.
What is that?
Big Bang Theory. You don't have to know now. Okay. 5. Light bends towards the normal when it enters. Towards the normal when it enters. A. From less dense glass to air. Are you sure? What? Yeah. A. You're all wrong.
What the?
The light bends towards the normal, means, guys, think about the angle made it to. If the light goes to the more denser medium, what happens to the angle? R gets smaller. So the more denser medium, answer is B. Yep. Remember, at water, the light get bended.
Yeah, I remember that, the fish one.
Yeah, fish one, exactly. Any questions? By the way, every single question, every single at this point is based on your school outcomes. So don't complain. Okay, that's basically covering that.